Hi, physics. Welcome back to another study of dynamics where we're going to be doing motion math. Woo! Math! Yay, math! Physics chapter 3b. Let's dive right into it. First equation that you need to memorize or be familiar with how to use is called the first equation of motion, and it is letting you figure out how fast you'll be going if you start at a certain speed and accelerate at a certain rate for a particular amount of time. So pretty straightforward concept. You're going at a certain speed, you accelerate for a certain amount of time, how fast you're going then. Lets you figure that out. So velocity 2, or sometimes called final velocity, equals velocity 1 plus the acceleration rate times the amount of time that you've been accelerating. Not the amount of time you've been traveling, the amount of time you've been accelerating. It looks very similar to the equation y equals mx plus b, and it graphs the same way. So this would be your y term, this is your b term, this is your m and x. And you can plot it all in and draw a graph just like you can using this old algebra friend here. Okay, and so that's a good way to use this equation. It's pretty straightforward. Let me give you some pictures here. If you were to graph rapid, steady acceleration like a jet fighter, you would have a straight line acceleration graph, and this is velocity and time. So your velocity is increasing as time goes on. You're going faster and faster and faster, versus in a train where you might be going the same speed for a very long amount of time. You'd have no acceleration, you'd have a constant velocity, right? Here we might have another line of acceleration that isn't quite as steep, something like a race car, not a jet fighter. And then there's increasing acceleration, where the rate of your acceleration is itself accelerating. So you are getting faster by getting faster with your fastness as you go in time. So this might be gently putting down on the accelerator and then pushing harder on the accelerator and getting faster and faster as you go. Okay, and then this would be an example of slowing down, where your velocity is dropping over time. Okay, several graphs there. Pause the video if you need to look at that more carefully. Here's an example problem. We have an aircraft carrier traveling at 35 knots, and it launches a fighter. Between the catapult's force and the fighter's engines, the rate of acceleration is 0.13 nautical miles an hour per second squared. Okay? If the fighter is accelerated at this rate for 3 seconds, what's the final velocity when it leaves the deck? So we need to make sure that we have our dynamics, our kinematics in place before we can do our dynamics. So let's choose a point of reference in the water outside the carrier. Otherwise, the carrier's 35 miles an hour don't count. Okay, so we're floating in the water watching this happen, and we're going to say positive direction is the direction that the carrier and the aircraft are moving, just so that our math is a little bit easier. Alrighty, now we have established that we're going 35 knots already because the carrier is going that fast, and we're going to move that into knots per second. So just a quick unit conversion from knots per hour to knots per second is 0.00972 knots per second. Okay. Velocity, the initial velocity is then that. My acceleration, I just realized I have a typo up here. It should be 0.0130, not 0.01. Yeah, there should be a 0 there. 0.013, and we're going to do that for 3 seconds, right? So we do the initial velocity plus the increase in velocity that was caused by this acceleration for this number of seconds. So we add that together, and this is my new speed. 0.04872 knots. That doesn't sound very fast, but that's knots per second. Turn that back into knots per hour, and we have 175.392 knots per hour. Now we can't leave it there because I have 3 sig figs, 3 sig figs, 3 sig figs. I need 3 sig figs, so let's call it 175 knots per hour. Okay, so that is the acceleration experienced by the jet and his new speed. Alrighty? Moving on. Determining displacement, given an average velocity and the unit of time. So remember, the bar over the V is the average velocity, and the bold-faced D there is my displacement, not my distance, my displacement. If you have an average velocity, then you can just say how fast I'm going on average for how long I've been doing it, and that's how far I've traveled. That makes sense, right? A car is moving at 20 miles an hour. For half an hour, it's moved 10 miles. Sounds like traffic on the freeway. If you have an initial final velocities but not the average, you can take the average all in one step. And so that's just adding the initial and the final velocities together and dividing by 2, right? That's just the average. Adding something together and dividing by 2. And then like you did before, you multiply it by time. So whichever forms of these are more useful to you, this is kind of the mother equation, and then this just lets you do another step at the same time. Okay? So that lets you know how far you've gone, if you know how fast you're going and how long you've been doing that. Okay? You can also calculate displacement by taking the area under the curve. So here's my velocity graph. Okay, if I'm traveling at a steady speed of 4 meters per second, okay, and I have been doing that for 15 seconds, I can just say 4 times 15 is 16 meters. Sorry, 60. I can do math, meters. But you can also notice that if you were to take this graph and treat it like a rectangle and say 4 times 15, the area there is 60. And that works here as a triangle, either direction. It also works under a curve. If you have taken calculus, you'll be able to calculate the area under a curve. If you've not, don't sweat it. We won't do that to you in this class. Okay, but in college physics, that will be required. Second equation, finding displacement given average acceleration, initial velocity, and time. So now again, we're looking for how far did you travel, but now we know the initial speed, how long you've been traveling, and then half of your acceleration for how long you've been traveling. T is the same value here. It's the value of the trip. This is distance knowing a steady acceleration, okay? So steady acceleration over a certain amount of time, how long did it take you? That's what this equation is. Go ahead and pause the video and write that down, but I'm going to keep trucking here. Let's use that equation. How long does the carrier's flight deck need to be, given the information from the last problem, as an absolute minimum to get the aircraft up to 175 knots? What does it take? Okay, so my initial velocity is 0. I'm going to only be looking at the activity on the deck this time. I don't care about the overall speed in air with regard to like some fixed point in the water. I'm only caring about what happens on the deck of the aircraft carrier. So my initial velocity is 0. Remember, I'm accelerating for 3 seconds at 0.013 knots per second squared. So here's my equation, copied from the last slide. If I plug it all in, my initial velocity is 0. He's sitting still on the deck. The aircraft carrier is moving, but our point of reference now is the deck of the aircraft. And this trip is going to take him 3 seconds, okay? Plus 1/2 times my acceleration times the 3 seconds again, squared. Let's take care of the square first, order of operations. The exponents come first. So now this is 9. Still 0. Well, it is 0 because 0 times 3 is 0. Now I have 0 plus the product of these numbers. So 0.0585 is what you get when you have 1/2 times 0.013 times 9. So my answer is 0.0585 nautical miles. That's how long the deck has to be. Let's turn that into something that's a little bit more usable for us. Let's convert that to meters. So if you convert that to meters, that's 108.342 meters. Okay? I have 3 significant digits. I have 3 significant digits. 108 meters long. That's the absolute minimum that a aircraft carrier's deck can be to have that operation occur. Pause the video if you need to look at that some more. Let's move on. The next equation we need is finding displacement when time is either not known or it doesn't matter. So this is, I started traveling at this speed, I accelerated at a certain rate, I ended up at this speed. How far did that acceleration take me? Not how long did the acceleration take me, but how much displacement did I achieve in this course of this acceleration. So this is the kind of stuff where saying like a sports car will get from 0 to 100 in the quarter mile. That's like the gold standard for super sports cars. If you can do 0 to 100 in a quarter mile, this is the equation that you would be demonstrating that with. Okay, so displacement equals final velocity squared minus initial velocity squared divided by twice the average acceleration. Bar over the top, average. Okay, so that's what we're doing. Pause the video if you need to write that down. Let's move on. What we're going to do with this particular problem is look at freefall, and that is a very common application of this equation. So we're looking at a known acceleration, which is the acceleration from gravity, and we're going to see how far do you fall before you've been going a certain speed. Or the other way to look at that is, if you fall a certain distance, how fast are you going? In order to do that, we need to know the standard acceleration of gravity. Now, it does vary a little bit from one point on the Earth's surface to another, but generally, the accepted value for the acceleration of gravity is 9.8. Your book uses 9.81. That's fine. 9.8 or 9.81 meters per second squared. So every second that you're falling, you're going 9.8 meters per second faster than the last second. Okay, so you jump out of an airplane. At the end of 1 second, you're traveling 9.8 meters per second downward. At the end of 2 seconds, you're traveling twice that, or 19.6 meters per second downward. At the end of 3 seconds, you're traveling another 9.8 meters per second faster than the last second. That makes sense, right? So you can substitute that number in for A for any of the equations that we've dealt with. Let's show you an example of that in working. Here we have a Navy SEAL in free fall. He's going to fall down and kick some butt and defend our country somewhere, and God bless him. In the meantime, he's falling. Terminal velocity for a skydiver in hard arch. This is the posture that he's in right now. That's called hard arch, as opposed to just tuck and dive, where you can get going faster. But the maximum speed for this is approximately 56 meters per second. That's really fast. How far does the skydiver fall while accelerating to that point? Okay, so not how many seconds does he fall, but how far below the plane is he when he achieves that speed. Okay, we're going to pick a point of reference on the ground below the jumper, and we're going to assign up as a positive value. So he is accelerating in a negative direction because he's going closer to the observer on the ground. Okay, so the displacement is getting less. He's getting the number of distance from him to the observer is getting smaller as he falls, right? So it's a negative acceleration, it's a negative displacement as he jumps. So here's my formula. D equals the initial velocity, the final velocity squared minus the initial velocity squared, and I have to answer the phone. And now through the magic of editing, you didn't hear that phone call. But we have the final velocity squared minus the initial velocity squared divided by twice the acceleration. Okay, so the final velocity is 56 meters a second. Initial velocity is 0. He was hanging there for a split second as he jumped out of the plane. Okay, 0 squared is 0. 56 squared is 3136. Now notice this was a negative number. It was a negative velocity. But when you square a negative number, you get a positive number. Okay. Now, twice the acceleration of gravity, negative 9.81, negative because he's going downward. Multiplying that by 2, it's still a negative number, negative 19.62. Now I divide this, and I get this wonderful number, negative 159.837 meters. So we need to correct for significant digits. I have 2 significant digits up here. I can only have 2 significant digits down here. Okay, so 160 meters. Now notice it's still negative 160 meters because he traveled in a negative direction. He traveled down, closer to the Earth. So he would fall downward 160 meters before achieving terminal velocity. That's section 3B. Post any questions in the comments. I'll see you tomorrow. God bless you. Have a wonderful day.